I think historically people have thought of universities as these ivory towers that are a bit isolated from reality. Increasingly, universities are collaborating with industry, having industry days, having senior design projects that are working on real design problems. And I don't know that that story is getting broadly out into the public. What was so exciting about this Texas A&M project is they had a really great team. They're bringing together different entities that all have the exact expertise needed to form a team that could do something that you couldn't do sort of individually. The combined expertise meant like, oh, they really could do something different here.
What we're building at Texas A&M University with the Roots program is the ability to put an instrument into the ground and image roots as they are in situ growing naturally in the soil. It's physics, soil science, genetics, plant breeding, all together trying to solve this problem.
Taking everything we've learned about signal processing and electrical engineering and physics to make a machine that could actually work in the ground. So we've really taken that idea, that sort of suite of technology and tools, and moved that into literally the great outdoors.
If we could do double duty with those plants and have them build big root masses in the ground, then it can help us address climate change. We identify the plant, cut the top off the plant so the roots are still growing naturally in the soil. Push a trench around the outside of the roots, and we lower the cylinder into the ground, which is actually the magnet. We can see all the water associated with the roots. So what you do is you get this image of the roots in the soil. And in clay soils, like we can see roots in agriculturally productive soils, which is where we can sequester carbon. Once we can see the roots, we can give information to the geneticists. And then the geneticists can link that up with the actual genetics in the plant and select plants that will build root architectures that we think are preferable for sequestering carbon.
What does give me confidence is they've had really good results so far, and that members of the team have a strong track record of really successful research.
Some university teams, PI has entrepreneurial focus, some not. And in many cases, like in the case of University of Maryland, the spin-off company was formed. So now we have a project when the university works together with a small company to implement this technology on a larger scale.
For me, getting a product to market is even more important than getting a paper published. I've actually had 3 different technologies that have gone towards the marketplace, from sensors to fuel cells and now solid-state batteries. One of the concerns that's happened is that because we're trying to get more and more energy density out of our batteries, we're pushing the limits in terms of the safety of the batteries. There tends to be a trade-off. What we've done is we've looked at, well, how can we replace the conventional battery technology, which uses a liquid organic electrolyte, which is a flammable mixture, with a solid electrolyte, which is completely non-flammable, and then completely removes the safety issue. Rather than having a liquid electrolyte that filled the space between the cathode and anode particles, we developed a ceramic structure that did the same thing. And that's what enabled us to get the energy density we have. We enable lithium metal on anode on one side, and we enable a much higher voltage cathode on the other side. Both of those result in much greater energy density per unit mass, per unit volume than compared to conventional batteries. The markets are huge, and for us it's going after the markets that make the most sense early on, but ultimately we think that we can dominate the entire battery space, and that is a very, very large market.
This technology has a huge potential because we all need a safe and energy-dense battery. And they proved, at least on a smaller scale, that it works. Now we are working with this team to prove that this technology will work on a bigger commercial scale.
I want to be a leading scientist. I want to teach the next generation of students, but I want to see what I've created become a commercial success.
Many people feel that our job as academics is to expand what people know about the world and publish scientific papers and then move on. But I feel a little different than that. If there are innovations, manifest technology, those devices that can come out of this research, I think, are critical.
What we really care about is impact, and like real impact. Like, how is this going to matter in the world? Not how is this going to create a publication that gets the most citations in the highest impact journal. It's what are we actually concretely contributing? It's so exciting to think about this thing that could touch everybody's lives. I mean, who knows what we're going to develop, that breadth of impact. I mean, it's pretty inspiring.